Hello viewers, welcome to IGCSE Computer Science Boolean Logic tutorial. Before you continue with this tutorial, you are encouraged to click the subscribe button and the notification bell to stay up to date with our recent relevant video tutorials. However, if you have any particular topic in computer science, ICT or mathematics that you would want us to make videos on, you are encouraged to make use of the comment box and state such topic. Without any further ado, let's get started with our tutorial. In this lesson, you shall be able to state the meaning and the rules of logic gates in a computer. Identify the standard symbols of different logic gates. State the functions of each different logic gate. Represent a logic circuit using a truth table and a logic expression. Represent a truth table as a logic expression and as a logic circuit. Represent a logic expression as a logic circuit and a truth table. Represent a problem statement as a logic expression, logic circuit, and a truth table. Now, what is a logic gate? A logic gate is a component in a computer system that controls the flow of electricity. A computer uses thousands of logic gates to output the high or low voltage that is needed to process and store that large quantity of data that it is provided with on a daily basis. You shall learn about 6 different types of logic gates, and they are NOT, AND, OR, NAND, NOR, and XOR gates. Note that logic gates can have several inputs, but will always produce a single output. I repeat, logic gates can have several inputs, but will always produce a single output. However, for the purpose of this lesson, you will be restricted to logic gates with a maximum of 2 inputs. It's important you understand the major role that a logic gate plays. A logic gate plays a similar role as a switch, which allows voltages to be switched to a high or low state. Then, what is a high or low voltage? The computer understands binary, and binary is simply a string of 0 and 1 values. So everything that is entered into the computer is interpreted as a string of zeros and ones. A high voltage, in this sense, simply means a 1, and a low voltage means a 0. Let's talk about the first logic gate that we shall be learning in this lesson, the NOT logic gates. And what are the characteristics or features of the NOT logic gates? Number one, it is the simplest logic gate. It has only a single input. It produces a single output. The output is a reverse of its input. That is, if an input of 1 is given, then the logic gate NOT reverses such input to 0. And if 0 is given as an input, the logic gate produces an output of 1. Here is the symbol of the NOT logic gate. The input and the logic gate NOT, which looks like a triangle and with a NOT before the output. The truth table for the NOT gate. The input combinations are 0 and 1. There are 2 input combinations. And how do you get the input combinations? The input combinations are actually 2 raised to the power n, where n is the number of inputs. So in this case, we have only one input in a NOT gate, and 2 raised to the power 1 equals 2. So there are 2 input combinations. However, it is not a needed or a required knowledge set for you to know how this input combination is gotten, because most times a table will be given to you in order for you to complete the output. So it is enough to know the rules guiding each logic gate. Having said that, the input, when the input of a NOT logic gate is 0, the output becomes 1. And when the input is 1, the output becomes 0. Here is the logic expression for the NOT logic gate. You can write the logic expression by first writing the output label equals the NOT operator and then the input label, or the output label equals bar input. So any one of these expressions is valid in representing the NOT logic gate. The second logic gate we shall be learning is the AND logic gate. And the characteristics are as follows. It has 2 inputs and 1 output. Remember, it is possible for a logic gate to have more than 2 inputs except the NOT gate, which must always have a single input. But for the purpose of this lesson, we are limited to cover the scope of 2 inputs per logic gate. So it has 2 inputs and 1 output. The output can only be 1 when both inputs are 1. So the most valid scenario where an output can be 1 is only when both inputs are 1, and every other thing becomes 0. The output is 0 when both inputs are 0, and the output is 0 when either of the inputs is 0. So the second characteristics specifies the major rule guiding the AND logic gate. The output can only be 1 when both inputs are 1. The symbol of an AND logic gate looks like a D with 2 inputs from the left and a single output on the right. Here is the truth table for an AND logic gate. And you can see we have 4 input combinations, or rather 4 rows. Okay, now these 4 rows are not gotten by random, but they are gotten from the formula 2 raised to power n, where n is the number of inputs. So in this case, 2 raised to power 2 equals 4. It is not a required knowledge set for you to know how this combination is gotten. It's just to suffice our learning module by mentioning that such formula exists, and the combinations you see here are not random. Most times you will be given a table to complete the output. So the logic expression for the AND logic gate is x equals A and B, or x equals A dot B. Now notice that in writing a logic expression for any given logic gate, the name of the logic gate is written in between 2 operands, and these operands are the inputs. For the case of the NOT gate has effect on only a single input. So you can actually refer to the NOT gate as a unary gate because it acts only on a single input at a time. The rest of the gates are binary gates because they have 2 operands, one on the left and one on the right. And of course, the name of the gate is always in the middle. The AND gate, the AND keyword in a logic expression for an AND gate is replaced with a dot. So you can actually write the expression as x equals A and B, or x equals A dot B. So any of these expressions is valid. The third logic gate we shall be learning is the OR logic gate. And here are the characteristics. It has 2 inputs and 1 output. The output is 1 when any of the inputs or both inputs are 1. Now the output can only be 0 when both inputs are 0. So I think the last characteristic is more specific and even simpler in explaining the rule guiding the creation of the OR logic gate output. The symbol is more like half of the moon, where there are 2 inputs on the left and a single output on the right. Again, the truth table for the OR logic gate has 4 input combinations, and of course you can see that the output is only 0 when both inputs are 0. Every other output becomes 1, as you can see. When A is 0 and B is 1, then the output becomes 1. When A is 1 and B is 0, the output becomes 1. When A is 1 and B is 1, the output becomes 1. So the output is only 0 when both inputs A and B are 0. The logic expression for the OR logic gate is X equals A or B, or it can be written as X equals A plus B, where the keyword OR is replaced by the symbol plus. The fourth logic gate we shall be learning is a negative logic gate of AND, and it is called the NAND gate, which simply stands for not AND gate. Here are the characteristics for the not AND gate. It has 2 inputs and 1 output. The output can only be 0 when both inputs are 1. The output can only be 0 when both inputs are 1. So it's more like a reverse of the output for the AND gate. Taking you back to what you've learned about the AND gate. The output of an AND gate can only be 1 when both inputs are 1. So the rest of the output becomes 0. But for the NAND gate, it is the opposite. That is, the output can only be 0 when both inputs are 1. The symbol of the NAND gate looks more like that of the AND gate, except that there is a negation symbol, which is identified as the not after the D before the output terminal. So 2 inputs on the left of the symbol, and of course a single output on the right of the symbol. This can be written alternatively as A and B. Then the output gotten from A and B is reversed using the NOT gate in order to produce the final output of X. So in other words, this NOT gate has reversed the AND gate, thus the NAND gate. Here is the truth table for the NAND logic gate. Remember, the output can only be 0 when both inputs are 1. And that is exactly what is here on the 4th row. So every other output becomes 1. Logic expression for the NAND logic gate is written in a similar way as other logic expressions, except that the keyword, which is between the inputs is now NAND. That is X equals A NAND B, or X equals bar A dot B. So any of these is actually valid. The fifth logic gate we shall be learning is the NOR logic gate, and the characteristics are as follows. It has two inputs and one output. The output can only be 1 when both inputs are 0. The output can only be 1 when both inputs are 0. So I will just take you back to the positive gate of the NOR gate, which is the OR gate. Remember, NOR gate stands for not OR gate, so it's a negative of the OR gate. Now, taking you back to what you have learned in the OR gates, the output for an OR gate will always be 1 when any or both inputs are 1. In other words, the output can only be 0 when both inputs are 0. Otherwise, every other output should be 1. Remember, the OR gate, in an OR gate, the output can only be 0 when both inputs are 0. The output can only be 0 when both inputs are 0. But the NOR gate is a negation of the output for an OR gate. So in other words, while the OR gate has its output as 0 when both inputs are 0, the NOR gate has its output as 1 when both inputs are 0. The rest of its output becomes 0. So the symbol here is more like that of an OR gate, except that there is a kind of negation symbol which is not before the terminal output. And this can be written alternatively as A or B using the OR symbol, and of course the output gotten is negated or reversed using the NOT symbol before the terminal output. The truth table for the NOR logic gate has 4 combinations, and of course the output can only be 1 when both inputs are 0, and this is for the NOR gate. You have to remember that the output can only be 1 when both inputs are 0. Otherwise, the output is 0. So every other thing becomes 0 except when both inputs are 0. So every other output becomes 0. The logic expression for the NOR gate is X equals A NOR B, or X equals bar A plus B. So A plus B are altogether barred using the bar symbol over them. The last logic gate we shall be learning for the purpose of this lesson will be the XOR logic gate. The XOR logic gate can also be written as the EOR logic gate, which stands for exclusive OR gate. Exclusive OR gate. Now here are the characteristics of the XOR logic gate. It has two inputs and one output. The output can only be one when any of the inputs is one. Now, alternatively, the output will be 0 when all the inputs are similar. So in that case, if you have two inputs of 0, 0, then the output becomes 0. When you have two inputs of 1, 1, the output becomes 1. So in other words, it is actually rendering the second characteristic to be more valid. The output can only be 1 when any of the inputs is 1, not when both inputs are 1. Very important. Now the symbol of the XOR logic gate looks more like that of the OR logic gate, except there is an arc before the logic gate. So A XOR B give rise to the output X. Now let's look at the truth table for this. The truth table for this is a table containing 4 input combinations. And of course, from what you can see, when two inputs are similar, 0, 0, A is 0, B is 0, then the output X is also 0. And when A is 1, B is 1, the output X is also 0. So the output can only be 1 when any and not both of the inputs is 1. So in this case, A is 0, but B is 1. Therefore, the output X is 1. And of course, when A is 1 and B is 0, then the output is also 1. The logic expression for the XOR logic gate is X equals A XOR B, or X equals A, then the symbol of the XOR gate is a plus inside a circle. So you have A XOR B as written on the slide. Now the next module of this lesson shall be completing the truth table for a given logic circuit. So we shall be learning how to complete. We shall be learning how to complete a truth table for a given logic circuit. Now, what is a logic circuit? A logic circuit is a combination of several logic gates that are linked to produce a single output. A logic circuit is a combination of several logic gates that are linked to produce a single output. The goal of this module is to ensure that learners learn how to complete a truth table for any given logic circuit. Now, the first example we have is to complete the truth table for the logic circuit. The logic circuit is given on the left, while the truth table to be completed is given on the right. So altogether we have about 3 inputs to work on, but of course the maximum of 2 inputs per a single logic gate. So in that case you have A and B going into the OR gate, and of course C going into the NOT gate. Now the output of A and B, A or B, and the output of NOT C both go into the AND gate to produce the output Y. So you have maximum of 2 inputs per logic gate. Let's proceed. Now, how do we complete the truth table for a given logic gate? Now we are going to start with A or B, and whatever output we have from A or B will be labeled as D, and whatever output we have from NOT C will be labeled as E. So D and E will altogether produce the output Y. Now let's look closely into this. D is A or B. Now we are working with this. We have the rule guiding the OR gate states that the output can only become 0 when both inputs are 0. So if any one of the inputs is 1, or even both inputs are 1, then the output should be 1. So in this case now, in the first row, A is 0, B is 0, of course D should be 0. A is 0, B is 0, D is also 0 on the second row. The third row, A is 0, B is 1, therefore D should be 1. The fourth row, A is 0, B is 1, therefore D is 1. 1, 0 give rise to 1. 1, 0 equals 1. 1, 1 equals 1. And 1, 1 again equals 1. So we are done with D. For E is whatever we have on C will be reversed to its opposite. So 0 for C changes to 1 for E. 1 changes to 0 for E. C is 0 and E is 1. C is 1, E is 0. C is 0, E is 1. C is 1, E is 0. C is 0, E is 1. C is 1, E is 0. So it's a reverse of whatever we have on C. Then we get E. Now our Y should now be D and E. Recall the rule for the D for the AND gates. The rule for the AND gate states that the output can only be 1 when both inputs are 1. So the inputs we are making use of here are D and E. Concentrating on D and E, we do not have 1 on the first row, so we have 0 as the output. We do not have 1 on the second row, we have 0 as the output. We have 1 1 on the third row, therefore we have 1 as the output. We do not have 1 here and 1 here, then we have 0. We have 1 here and 1 here, we have 1. We also have 1 and 1 on the second to the last row, we have 1 as the output. So the rule, I state again, is that the output can only be 1 when both inputs are 1. The next module we shall be working on is writing a logic expression for a logic circuit. What is a logic expression? A logic expression is a Boolean equation of a given logic circuit. The goal of this module is to ensure that learners learn how to convert a logic expression from a given truth table, or better still, how to write a logic expression from a given truth table. To write a logic expression, the following syntax must be followed. You first write the output level, then equals input 1, the name of logic gate, then input 2. An example is X, which is the output, equals the first input A and the second input B. Now the AND is the keyword for the name of the logic gate. The first example we shall be working on this particular module is as follows. Write the logic expression for the given logic circuit. Then you have the circuit written, which is P NAND Q. The second one is have Q, that is not Q, going into the XOR gates. Now the output of P and Q and the output of not Q both go into the logic gate XOR, alright? And whatever that is gotten as the output at this level is taken into the AND gates together with the R input in order to produce the Z output. Step 1. Count the logic gates in the logic circuit. So I have started my counting. The first logic gate I've counted here is the NAND gate. The second is the NOT gate. The third is the XOR gate. And the fourth is the AND gate. Step 2. Derive logic expressions for each of the logic gates. Okay. The logic gate 1, which is the NAND logic gate, has P NAND Q. As you can see, Q is going into the NAND gate together with P. So we have P NAND Q. The second one is a unary logic gate, which is a NOT. So it becomes NOT Q, as you can see. Now the third one, which means the third one, which is the XOR gate, is taking whatever I have from the first logic gate together with the second logic gate, and combining them using the XOR. So as you can see, the first one is P NAND Q. So I have it here, enclosed within parentheses, XOR, which is the main gate itself here at this level, and the second logic gate, logic combination. So we have NOT Q. The fourth logic gate is this. So whatever I have at the third level is combined with the value of R. So I have P NAND Q XOR NOT Q all together combined using AND gate with R. Therefore, I have Z equals P NAND Q XOR NOT Q, and with this parenthesis, and R. Now, it's very good you make informed use of the parentheses and the square brackets in order to differentiate what you're dealing with. So as you can see, the first logic gate combination I enclose within parentheses before combining it with the second logic gate at the third level logic gate. So, and of course at the fourth level logic gate, I have to enclose whatever I got from the first 1, 2, 3 within a square bracket before combining with an R input. The next module we shall be working on is to write a logic expression for a truth table using NOT, AND, and OR gates. Example 1. Write a logic expression to represent the truth table, and this is the truth table here. The first step, we shall be analyzing and comparing the outputs with reference to the rules for the different logic gates. Now, what this basically means is that you recall the rules for all the logic gates, all the different logic gates you have learned in the past, and compare those rules with what seem to apply on this truth table. Does this truth table look similar to any of the logic gates? Now the answer is of course no, because it doesn't look similar. So you're comparing the rules. The best way to do this is to recall the rules. For the NOT gate, of course, NOT gate applies to only a single input, so this is actually invalid for the NOT gate. And the second is the AND gate, which states that the output can only be 1 when both inputs are 1, otherwise every other output should be 0. So, and of course this doesn't apply here, because when both inputs are 1, the output is not 1. The next one is the OR gate, which states that the output can only be 0 when both inputs are 0. Otherwise, the output should be 1. So it doesn't apply here. We only have 1 output instead of 3 1 outputs. So the third one is a kind of negation of the NAND gate, which is the output becomes 0 when both inputs are 0. So Otherwise, every other thing should be 1. So it doesn't apply here. And the NOR gate states that the output becomes 1 when both inputs are 0. So it doesn't apply here. And of course, the XOR gate states that the output becomes 0 when both inputs are similar. So we have 0, 0 at the first level, we have 0. And we have 0, 0 at the first level, 0. So we do not have 1 here, so which violates the rule. Okay, so we can only have 0 when both inputs are similar. So inputs are not similar at the third level, but we have a 0. So in that case, this violates the rule. We can actually conclude at this point that this table doesn't look similar to any of the logic gates, the standard logic gates we have learned. Let's proceed to step 2. Now, if step 1 fails, identify rows with the output value of 1. So we have identified the second row to be the only row with the output of 1. Now, step 3, identify the input with a 0 value and reverse its value to 1 using NOT gate. Now, the next step we're going to do, you will know why we have to make use of the NOT gate to reverse this. In the next step, I shall let you know why we have chosen to do this. Okay. Now, the fourth step is to combine the inputs using AND operator and assign to the output. Now look at this. Because we intended to actually combine this, that is A and B, using the AND gate, alright, in order to produce the output of 1. Recall that 1 can only be produced using an AND gate only when both inputs are 1. So originally we have 0 for A. In order to make A to be 1, we have to make use of the NOT gate to reverse the input of A. So having done that, NOT A at this point becomes 1. So 1 and 1 gives us 1. So in that case, our expression now changes to X equals NOT A and B. So that is what we have at this level. Example 2. Write a logic expression to represent the truth. Now in this truth table, it doesn't look similar to any of the logic gates that we have solved in the past. So, and we have two rows whose outputs are 1. So we are going to combine this in a more advanced way than what we just concluded when we have 1 row giving us a 1 output. Alright, step 1. Provided the table is not similar to those of standard logic gates, identify rows with the output value of 1. So we have identified row 2 and row 4 with the output value of 1. Identify the input with a 0 value and reverse its value to 1 using NOT operator. So we have only one input that has a 0, okay, and we have reversed it to NOT A. Combine the inputs in each row with an AND operator. So each row we have NOT A and B. And why are we having NOT A? Because 0 has to be changed to 1. So in that case, we have to apply the NOT A to change that 0 to 1 before we can add it to B using the AND gate. Now for the fourth one, We do not have to change any input. So A is 1, of course, we just write A, and B is also 1. We write B as well. The fourth step is to combine the outputs from each row with an OR operator and assign to the output. So in that case, we have two different expressions from each row, and we have to combine these expressions using the OR gate. So X, which is the output, equals the first expression, not A and B, enclosed within parentheses, and combined using an OR gate with the second expression, which is A and B in parentheses. So you have to take note that this is the first expression gotten, and we are combining it using the OR gate with the second expression gotten. It's always recommended that you enclose each of the different expressions in parentheses. Example 3. Write a logic expression to represent the truth table. Now this truth table has three main inputs, and of course, because it has three main inputs, we have about 8 input combinations, because 2 raised to the power 3 equals 8. Now again, it's not necessary you know about this, but if you want to move further with your own research, you can also do so. Alright, we are going to proceed with the steps. Step 1. Provided the table is not similar to those of standard logic gates, identify rows with the output value of 1. So we have about 3 rows with the output values of 1. Now combine the inputs for each row from step 1 with an AND operator. So with what we know already, each row, the inputs for each row must be combined using the AND gates. So we have row-wise combinations using AND gates, and for AND gate to be valid, all the inputs must be 1. So A is 0 here, we have to change it to 1 by using not A. B is 0, we change it to 1 by using not B. And C is 1, so we leave it as it is. And we have AND C. The next one we have is A is 1, we leave it as it is, A, and B is 0, we change it to not B, and C is 1, we leave it as it is. And the third one is everything is actually 1, so we leave them as they are, and they become A and B and C. Step 3. Combine the expressions from step 2 with an OR operator and assign to the output. So we have these 3 expressions. We have to actually combine them using OR operator. So in this case, I am actually taking my time to differentiate how this combination is done. So this is the first expression, combine using OR with the second expression, and combine using OR with the last expression. Now notice that each expression is enclosed in parentheses. So it's recommended you enclose each in parentheses before combining. Alright? Okay. So therefore, we have a single line of the output X equals not A and not B and C or within parentheses, or A and not B and C all within parentheses, or A and B and C all within parentheses. The next module we shall be learning is to draw a logic circuit from a truth table or logic expression. Example: draw a logic circuit to represent the given truth table. Now we have this truth table. How are we going to draw a logic circuit? Now, step 1 is to write a logic expression for the given truth table. So we already know how to write a logic expression from the immediately concluded module before this one. So if you are still finding it difficult to do so, I encourage you to just go back to the module and learn more about it. Okay? So having done this, draw the logic circuit. So how do we draw the logic circuit? We take them bit by bit. Okay, we have not A and B. Alright, not A and B. So we have A negated, so which gives us not A. Okay, so we have not A here, and our B, this is B. Okay, this is our B, and B is coming from here. So it doesn't really matter where your B is coming from, but it's important you have to do this strategically. Alright, so B is coming from here, and of course we have OR. So the OR gate is what we have here in between A and B. So we have A is coming from here and B. So just master the craft of drawing this so it doesn't look so clumsy and disorganized. So we have about 1, 2, 3, 4 logic gates. Okay, so very important. The last module, hopefully, we shall be learning is the problem statements. And the problem statement is actually where you are tested on how to apply the knowledge you have gathered. How do we apply this gathered knowledge? This question might look a bit confusing at this point, but it's going to be of less hassle when we are done with this module. So quickly, the first example we shall be working on is a factory manufactures soap and has a system that monitors the manufacturing process. The system has 3 conditions to monitor: the acidity A, the temperature T, and the pressure P. The conditions for the system are input, binary value, and condition. So A, which is acidity, when the binary value for A is 1, okay, then the condition is that pH is less than or equal to 7. When the acidity binary value is 0, the condition is pH is greater than 7. And of course you have that for T and for P. Now let's look at how this problem can be solved. The system will sound an alarm X when certain conditions are detected. So there are conditions for an output X to be produced. The alarm will sound when, now what are these conditions? The conditions are when the pressure is greater than or equal to 75% and the temperature is greater than or equal to 50 degrees Celsius, or the temperature is less than 50 degrees Celsius and the pH is greater than 7. The question we have here is, write a logic expression to represent the problem statement for the alarm system for the soap manufacturing factory. Solution. Step 1. Using the information in the table, derive a logic expression for each of the alarm conditions. Now, what are the alarm conditions? To remind ourselves, the pressure is greater than or equal to 75% and the temperature is greater than or equal to 50 degrees Celsius, or the temperature is less than 50 degrees Celsius and the pH is greater than 7. A logic expression for the alarm conditions. We have to actually derive the logic expressions. We have alarm condition. The first condition we have identified is pressure is greater than or equal to 75%. And when pressure is greater than or equal to 75%, what is our input like? So we have pressure greater than or equal to 75, then P is 1. So in that case, we just have P. When temperature is greater than or equal to 50 degrees Celsius, let's look for it. Temperature is greater than or equal to 50 degrees Celsius. The value of the binary for T is 0. In that case, it becomes not T because the binary value is 0, not 1. So we have not T in this case, not T. The third condition, temperature is less than 50 degrees Celsius. Where do we have it? Temperature is less than 50 degrees Celsius. So because the binary value of T is 1, then we have T here. pH is greater than 7. Where do we have pH greater than 7? pH is greater than 7, then A is not A because the binary value is 0. So we have not A. Alright. Step 2. Combine individual logic expressions using appropriate operators. Now the logic expression for the alarm conditions gotten as follows here. Now the alarm condition, this, we have pressure greater than or equal to 75 and the temperature is greater than or equal to 50 degrees. So we are working on the AND gate. So what is this? Pressure greater than or equal to 75 is P. We have P and we have AND, okay, and that is why we have AND here. The temperature is greater than or equal to 50. Where is it? Temperature greater than, we have not T. So we have P and not T. Enclosed within parentheses. Before we have OR, this OR here, replaced here with the OR gate. Okay? Now temperature is less than 50 degrees Celsius. Temperature is less than 50 degrees Celsius, then the value is T. We have T and the pH is greater than 7. pH greater than 7 is not A and not A. So this is how to actually deal with this So it requires your carefulness and attention to details before you can be able to walk through it. Okay, so we've come to the end of this tutorial, and of course, to stay up to date with more videos that are as resourceful as this, you are encouraged to subscribe and stay tuned for more resourceful videos. This video is brought to you courtesy of EduHub Intellectual Resource Center, and we are a body that is interested in making sure that education is not a far reach for so many people, so you can actually get resourceful content from our channel. Make sure you subscribe, and you can share this video with so many people you think might be interested to learn, and whom you think that this video might be of help to. See you in our next video, and please ask your questions in the comment box if you have any. Thanks for watching.